Now I could continue subdividing my angles. Okay, so here I've got an angle that subdivides this angle between 0 and 1, another but the angle between 0 and 2, and so forth. And I've filled in all these angles all the way around here. Okay, so with this new subdivision, I've divided the entire circle, and I haven't drawn in the division for the lower half of the circle, but you can imagine what that would look like. I've divided the circle into 32 segments, 32 angles, 32 arcs, which means that I've divided my interval from 0 to 2 pi radians into 32 pieces. 2 pi divided by 32 is pi over 16, so we could say that each of these angles is pi over 16. So I don't think I'm going to write that down, but I've got pi over 16, 2 times pi over 16, which is pi over 8, 3 pi over 16, 4 times pi over 16, which is pi over 4, etc. I could write all those angles down as multiples of pi over 32. 1, 2, 3, 4, 5, 6, 7, all the way out to 31 over 32, reducing when we need to. And I recommend that as an exercise, that there's something you really need to understand, that you'll understand if you just do that. It wouldn't take you 5 minutes to write all those fractions down and reduce them. So, just a suggestion. And of course, then each of these angles is accompanied by its projection, or by a projection of the corresponding point on the arc on the y-axis, giving us new values. And of course, I could have, indicated those values here, and giving us new points on the graph. So I'd have a point here, point here, point here, and a point here. Each of these points, new points, being halfway in the horizontal direction between two existing points. And if we move up from here to here, each of the points is a little more than halfway to the previously labeled point. So this point is a little more halfway from here to here, this is a little more than halfway from here, and so forth. And of course then we can do the same thing for the whole cycle. Now we don't have to stop there. We can continue subdividing. I'm not going to attempt to do that. First of all, it'd be a lot of drawing. Second, the picture would get really cluttered. But we can continue subdividing forever, indefinitely, which means we can get an indefinite number of points here. We can make the points as close together as we wish. So we can keep subdividing we can get the graph points as close as we wish. And this important by construction, because every bisection can be done by a compass and straight edge construction. So in that sense, we can construct practically all of this graph. We can construct what we would call, if we think of taking this process on forever, we would end up with what's called a dense set of points. A set of points that's as close as we might desire to any other given point on the graph, whether that point is constructed or not. So we can extend this construction beyond the angles that we can actually construct, beyond the points that we could actually get on the graph by construction. And that's kind of a big deal mathematically. I'm not going to say any more about it right now, but that gets into some fairly deep mathematics beyond the depth of a calculus course. But it's an important idea, and it's one that's kind of neat because you can't actually do this with a power or an exponential function. So Now, I haven't actually gone through a proof that you can't do this with the power and exponential function, because I think you just about have to work out the details of the Galois theory. If you understand that theory, the details are fairly straightforward. And the Galois theory is an extremely deep theory in mathematics. You have to study mathematics for at least 5 years after calculus before you have a good command of the Galois theory, unless your IQ is 160 or more, in which case you probably do it pretty quickly. So not something we're going to talk about. And I couldn't work out the Galois theory right now without reference, and probably a lot of reference. Okay, so this whole idea, again, that we can continue subdividing this and get a set of what I call dense points. It's a mathematical term, dense points on the graph. A dense set of points on the graph, not a set of dense points. None of the points is dense, but the set of points is what we call dense. Very interesting idea, and worth just giving a little thought about an overall concept that will arise once more if you go into a fair amount of depth in your study of mathematics.